Constructionally, transformers are classified as core type transformer and shell type transformer. These two types are classified based on the way by which the winding is placed on core. In simple, core type of transformer means winding surrounds the core. So if suppose this is the transformer core and winding surrounds the core means this is what? Let us suppose this is the winding. And whereas in case of shell type of transformer, in simple, here core surrounds the winding. That is how means if suppose this is the transformer core of shell type transformer and this is the core, and in this case winding will appear to be surrounded by the transformer core. So winding will be placed on the center of the limb. So these are the HV windings and these are the LV windings. So these windings are surrounded by the core. So this is how the transformer is classified based on the way the winding is placed on the core. So in core type of transformer there are two limbs, and here in shell type there are three limbs, and in core type of transformer these two limbs are of equal area of cross section, whereas in shell type of transformer the outer limbs are of half of the inner limb area, and here the leakage flux is more, whereas here in this case leakage flux is less. So in this case power transfer capability is low, whereas in this case power transfer capability is high because leakage flux is less, and in this case the winding required is more, that is copper material required is more because these are placed horizontally, whereas in this case as windings are placed vertically winding material required is less, and in this case concentric type of winding used, whereas in this case sandwich type of winding is used. And the other difference is it is a series magnetic circuit, because in this case there is no flux division, whereas in this case it is a parallel magnetic circuit, because here flux division will take place. And in core type of transformer insulation required is less, that is insulating material is very low, and in this case insulating material required is more. And the other important difference is of these two type of transformer, core type of transformer is preferred for high voltage applications, whereas shell type of transformer is preferred for low voltage applications. Of course, it is known that we can obtain these similar characteristics from the core type of transformer and shell type of transformer, but the choice between the type of transformer depends upon many factors. That is, it can be on kVA rating, or it can be on losses, or it can be on insulation, or etc. But please keep in mind that for high voltage applications core type of transformer is preferred, and for low voltage applications shell type of transformer is preferred. And of these two, the important difference that to be discussed is about the radial forces and axial forces. Now let's discuss that. Transformer windings are form wound. Form wound means they are wound on a separate structure to fit on the core. So if suppose this is the form wound winding, and now transformer core is placed in it. Generally for small rating transformers, transformer winding is of square shape or cylindrical shape, and the transformer core is of square shape. And for higher rating transformers, transformer winding is of cylindrical shape only, because for cylindrical shape of winding mechanical strength is more, and the core cross section is of cruciform, that is it will look like this, which is having many steps. So transformer core cross section for higher rating transformers will look like this, and for high rating transformers these steps of cruciform are increased. The type of winding employed in core type of transformer is concentric winding, whereas in shell type of winding the type of winding employed is sandwich type. Concentric winding means here both HV winding and LV winding are having same center. That is, if let us suppose this is the limb of the transformer and this is the other limb of the transformer core. So first there will be an insulating cylinder on the transformer core, and on which LV winding is wound. So half of the LV winding is on one limb and remaining half of the LV winding is on the other limb. And now again there will be an insulating cylinder on which the half of the HV winding is wound and remaining half of the HV winding is wound on the other limb. So this is the insulating cylinder on which HV winding is wound. So if you observe here, both LV winding and HV winding are having same center. So this type of winding is called concentric winding, and concentric winding is further classified into three types, that is crossover winding, helical winding, and disc type winding. Okay. Crossover winding means, let us suppose this is one layer of coil, and to add another layer continue the winding on this. So this will be the second layer, and similarly to make multiple layers continue the winding, and finally this coil section will have an inner terminal and an outer terminal, and similarly there will be another coil section which is having inner terminal and outer terminal. So in crossover winding the outer terminal of one coil section is connected to the inner terminal of the another coil section which is adjacent to it, and crossover windings are mostly preferred for HV side of the low rating transformers, that is for less than 20 amperes. Crossover windings are used. Next, helical winding. In helical winding, winding consists of rectangular strips which are separated by an insulating layer, and which might consist of number of parallel rectangular conductors which together form a single conductor. That is, let us suppose this is the cross section of the conductor which are having many number of conductors separated by an insulating layer. So this together will form a single conductor in helical winding. In this type of winding, the winding is wound in the form of helical layers. That is, if suppose this is the transformer core, and this is, let us suppose this is the conductor, and these are the windings which are placed on the transformer core. So if you observe this, this will look like a spring which is having a spiral shape. So is why the name given to this type of winding is helical winding, and this is the single layer winding, and to get double layer the winding is wound in opposite direction. So here the winding is like this for single layer winding, and for double layer winding will be wound like this. And helical winding is preferred for LV side of the high rating transformers. Next, disc type winding. This is the winding which is employed in power transformers and distribution transformers, and this type of winding consists of rectangular strips. And disc type winding means the winding is wound from the center to outwards to form a disc, and then again it is wound to form another disc from inner to outerwards. So similarly there will be number of discs present and which are wound like this, and they form a disc type winding. Next, coming to shell type of transformer, sandwich winding. Sandwich winding means here LV winding is sandwiched between two HV windings. So if this is the central limb, and let us suppose this is the HV winding, and let us suppose this is the LV winding, and let us suppose this is the HV winding, and let us suppose this is the LV winding, and let us suppose this is HV winding. So if you observe here in sandwich winding, LV winding is sandwiched between HV windings. So this type of winding is called sandwich winding. Now let's discuss about the radial forces and axial forces. That according to Lorentz principle, that two windings will have opposite forces acting on each other. That is, if suppose this is the current carrying conductor, and let us suppose this is the current carrying conductor, and these two conductors are having current flow in same direction. So the magnetic field direction along this conductor will be in anti-clockwise direction. So if you observe here that the flux between these two conductors is weak, and in this portion the flux is strong. So the force direction is from stronger to weaker flux. So here attractive force exists between the two conductors which are having current in same direction. And let us suppose this is the current direction in one conductor, and let us suppose this is the current direction in another conductor. So this conductor will have the magnetic field in anti-clockwise direction, and this will have magnetic field in clockwise direction. So if you observe that the flux between these two conductors is aiding, so this is having this direction and this is having this direction. So flux is aiding, means the flux between these two conductors is strong, which means the outer flux is weak, and this is also weak. So here the force direction is outwards, that is repulsive forces exist between these two conductors which are carrying current in different directions. So in case of transformer, the forces existing between the two windings are repulsive forces, because HV winding and LV winding are placed on the same limb. So in core type of transformer, let us suppose this is the core, and which are having repulsive forces, and if N1 I1 is equal to N2 I2, these repulsive forces are equal, as N1 I1 and N2 I2 are equal and are acting in opposite direction. So there is no radial force. Radial force is equal to 0. But if N1 I1 is not equal to N2 I2, that is repulsive forces are not equal and they are acting in opposite direction, then there will be axial force coming into picture. So if axial forces come into picture, both HV winding and LV winding positions will get slipped. That is, the winding becomes unstable. So to secure the HV winding and LV winding in their position, N1 I1 and N2 I2 must be equal. And similarly in sandwich winding, here there will be opposite case. That is, we know that sandwich winding means LV winding is sandwiched between two HV windings. Let us suppose this is the sandwich winding, and if you observe that here the forces acting on this direction and this directions are unequal, because here the extreme end is HV and here the extreme end is LV. So this force will be more and this force will be less. So is why axial forces are unequal. So if axial forces are unequal, then radial force will come into picture. So if radial forces comes into picture, then the windings becomes unstable. Therefore, to make the winding stable, the solution here is that we must make the axial forces equal on the both sides. So if you place the half of the LV winding of a section and remaining half of the LV winding of that same section in the other end of the transformer, then axial forces will get equal. So if axial forces are equal, then their radial force is 0, so that the HV winding and LV winding are secured in their places. So that the main difference between the core type and shell type winding are that here, because of the unbalance, that is because of N1 I1 not equal to N2 I2, here axial forces come into picture. And in case of shell type of transformer, here if axial forces are not equal, then radial force will come into picture, which will make the winding unstable. So to make the winding stable, here in case of core type of transformer, N1 I1 must be equal to N2 I2. And to make the winding stable, in case of shell type of transformer, half of the LV winding of a section to be placed at one end, and remaining half of that section of L winding must be placed on the extreme end.